Suppose we have a vector space V. We said that one of the properties of a vector space is that for all vectors inside your vector space, there exists a vector 0 in the vector space such that x plus 0 is equal to x. And this vector 0 is really special because this is actually a unique vector. There's only one vector that has this property, that when we take any other vector and add it to this vector, we get the original vector back. I want to prove this. I want to show that this vector is actually unique. So show that in a vector space, the 0 vector is unique. And how I'm going to do this is I'm going to use a proof by contradiction. I'm going to assume that there's more than one vector that acts like the 0 vector. And so if there's more than one, then there's going to be at least 2 of them. So what we're going to do is we're going to assume V is a vector space in which there is a vector, we're going to call it 0 sub 1, and another vector 0 sub 2, such that for all vectors x in V, we have these properties. 0 sub 1 plus x is equal to x, and 0 sub 2 plus x is equal to x. Well, this is true. Now remember, this x is any vector in your vector space, including the 0 vectors. So notice zero sub 1 plus 0 sub 2 is equal to 0 sub 2 by this first property here, where I'm letting x equal 0 sub 2. But at the same time, using the second property, we have 0 sub 2 plus 0 sub 1 is equal to 0 sub 1. So this is when x is equal to 0 sub 1. But we also know that vector addition is commutative. This is one of the very first properties of a vector space, which tells us 0 sub 2 is equal to 0 sub 1. So now we have a contradiction. Because we were assuming that there were 2 vectors that had this property. Now we've shown that there's only one. So therefore, the 0 vector is unique. Okay, let's move on to section 3.2, which is called subspaces. So say we have a vector space V, and I'm going to take a subset of that vector space. So I'm going to pull some vectors from it. It may not be the entire vector space. I could take the entire vector space, but usually we have a smaller set than the original space. So we want S to be a non-empty subset of a vector space, and we want this subset to satisfy 2 conditions. The first condition is if alpha is a scalar and x belongs to your subset, remember it's non-empty, then alpha times x is also a vector and it belongs to your subset. So this is saying we're closed under scalar multiplication. Inside of S. The second property is if x and y are 2 vectors in your subset, then x plus y belongs to your subset. So here we're closed under vector addition. So if you have a non-empty subset that satisfies these two properties and is a subset of a vector space, then we say S is a subspace of V. So it's a vector space inside a bigger vector space. S inherits all other vector space conditions because S is a subset of V. So in other words, we had 10 properties for something to be a vector space. 8 of those properties are already inherited for S because it is a subset of V. And being a subset of V, you get all of those properties for free. But the 2 properties that you don't get for free is these right here, 1 and 2, which is being closed under scalar addition and scalar multiplication and vector addition. So you don't get those for free. So you have to check those 2. And if those 2 hold, then you have a vector space S inside this larger vector space V. And the smaller vector space is called a subspace.